Hi, today we're going to talk about how the derivative, the first derivative and the second derivative, the information from those derivatives can help you sketch a graph. So first let's talk about the first derivative. So if you look here on the left of the screen, when the first derivative is positive on an interval, then the function is increasing over that interval. When the second derivative is negative on an interval, then the function is decreasing. And when it's equal to 0, well, that's where we find critical points, which could be either a maximum, minimum, or they could possibly also be or it could be an inflection point. So remember that if you have a critical point, if the derivative changes from positive to negative to the left and right of that critical point, then you have a maximum. When the derivative changes from negative to positive, then you have a minimum at that critical point. And if it does not change before and after that critical point, then it is neither a local maximum nor a local minimum. So we'll talk more about how to find test points to determine if it's positive or negative once we do an example. So before we go on to the example, let's talk about the second derivative and concavity. So when something is concave up, that means it would have a shape something like this, like a traditional parabola, or it could be more subtle like this. That's still considered to be concave up. And a function is considered to be concave down if it's looks like an upside down parabola, or again, it could be more subtle, something like this. So those two would be considered concave down. An inflection point, if we go a little further down, an inflection point occurs when a graph changes from concave up to concave down, or from concave down to concave up. So for example, something like this would have an inflection point because, and I would guess it's about here, for example, because the graph changes from concave down to concave up. All right, so how do we find those? We find inflection points and intervals of concavity by taking the second derivative and setting it equal to 0 and solving that equation. So when we solve that equation, you then again need to take test points and see if it's positive or negative to determine if it's concave up or down. And again, a change in sign from concave up to concave down would determine whether it is an inflection point or not. So to review, extreme points, inflection points, and information on intervals tell you if the graph is increasing, decreasing, concave up, or concave down. The first derivative is used to identify critical points and determine where the function is increasing or decreasing, and it will also help you to find maximum and minimum values if they occur. And the second derivative is can also be used to determine maximum and minimum values, but it's also used to determine concavity and possible points of inflection. So let's look at an example of where we'll use both the first and second derivative to get good information about a graph, and then we'll sketch the graph. So here's our first example. We're going to use the first derivative to find intervals of increasing and decreasing and maximum and minimum points for the function below. So the function here in pink is f of x equals 2x squared minus 6x squared plus 1 equal to 0. So we're going to go ahead and take the first derivative. The first derivative is 6x squared minus 12x equals 0. So to solve this, we must factor. So we get 6x times x minus 2 equals 0, leaving us with two solutions, x equal to 0 and x equal to 2. Now, x equal to 0 and x equal to 2, those are now the points that we have to keep track of, and we use a number line to keep us organized. So here I put 0 on the number line, and here I put 2 on the number line. And so our test points are values to the left of 0, so something like a negative number is fine. And so I'm going to take a test point and plug it into the first derivative. So the easiest place to calculate the value is right here. And you don't really need to know what the value is. All you really need to know is what is the sign of the first derivative on that interval. All right, so suppose we pick -1 as a test point to the left of 0. So if I plug in -1 here where I drew the arrow, then I will get 6 times -1, well, that's negative. And then plug in -1 here, -1 minus 2, that's also negative. A negative and a negative makes a positive. So I indicate that here to the left of 0 on the number line. I say that to the left of 0, it is positive. And I draw an arrow going upward to show that when it's positive, it is actually increasing. The function is increasing. Then you pick a test point between 0 and 2, such as 1. And again, plug it in to the first derivative. So if I plug in 1, you get 6 times 1 is 6. Plug in 1 here, 1 minus 2, that gives you a -1. So positive 6 and -1 gives you a negative result. And negative means that the function is decreasing. Then again, pick a point greater than 2, such as 3. Go ahead and plug it back into the first derivative, and you also get a positive result, which means the graph is increasing. So to summarize, that means that the graph is increasing from -infinity to 0, and then from 2 to infinity, and it is decreasing on the interval from 0 to 2. So keep in mind that intervals of increasing and decreasing are always open intervals, because at the endpoints at 0 and 2, that's when the derivative is equal to 0, and that's where you have a tangent line that's 0, which means the graph is neither increasing nor decreasing. So this also means that we have both a maximum and a minimum value. So we have a maximum at 0, and when x is 0, your y value is 1. And we get the y value by plugging it back in here, in your original function. So if you plug in 0 into the original function, you get that the y value is 1. So that's our maximum value. And you know it's a maximum because the graph went up and then back down, so therefore 0, 1 is your high point there. Then we have a minimum value at 2, and the function value at 2 is -7. Again, you would plug in 2 right here, and if you do and resolve it, you get that the y value is -7. And 2 -7 is considered a minimum because the graph is decreasing, then increasing again at 2. So that already gives us a lot of good information to graph the function, but we're going to get a little bit more by using the second derivative. So part 2 of the same problem says, to determine the concavity of the function, identify the inflection point or points, then sketch the graph for f of x. So recall that f prime is 6x squared minus 12x. We found that in the previous work that we did. The second derivative is 12x minus 12, and we set that equal to 0. So factor out a 12, and so 12 times x minus 1 equals 0, giving us one solution, x equal to 1. So similarly to what we did before, we put 1 on a number line to help us stay organized. Only 1, because we only got one solution. And so now I need to take a test point to the left of 1 and to the right of 1, and this time we're going to plug it into our second derivative. And so here is the most convenient place to plug in to determine if it's positive or negative. So if I pick something less than 1, like 0, that would give me a negative result. A negative result, when you're using the second derivative, means that your graph is concave down. It's facing downward. Then if we pick a number greater than 1, like something on the right, such as 2 or 3, it doesn't matter what you pick, plug it into the second derivative, and that would give you a positive result, which means your graph is facing upward, concave up. So to summarize, the second derivative tells us that the graph is concave down from -infinity to 1, concave up from 1 to infinity, and we have an inflection point. An inflection point is a point where the graph changes from concave down to up or from up to down. So this one is changing from concave down to up, and when x is 1, f of x is -3. Again, we find the actual point on the graph by returning back to the original function right here. So if you plug in 1, you will get -3 as a result. All right, so now we need to sketch this And when we do, we're going to use our first and second derivative. So just to remind you, the first derivative said that it is increasing from negative infinity to 0. So let's see if that works here. This is increasing from negative infinity to 0. So we see that right here. And then it was decreasing from 0 to 2. So we see that right here. And then it's increasing again from 2 to infinity. So the first derivative is certainly reflected here. Let's look if it matches with the second derivative. Second derivative told us that it's concave down from negative infinity to 1. So this certainly looks like it is concave down from negative infinity to 1, and then it transitions to concave up from 1 to infinity. And we have an inflection point at 1, -3. So I made my inflection point purple, and my green points are maximum and minimum points. So we have a maximum at 0, 1, a minimum at 2, -7. Again, going back to our first derivative, that's exactly what we saw there. So we get a lot of good information from both derivative tests. All right, so let's do another example. This time we'll do a rational function. And again, we'll use both the first and second derivative to help us get a good sketch. So here the directions say, determine the intervals of increasing and decreasing, maximum and minimum points, intervals of concavity, and inflection point or points for the function below, then sketch the graph. So we have a rational function y equals -1 over 1 minus x squared. So here, with rational functions, you're going to have to keep something in mind, because with rational functions, you sometimes have restrictions on the domain. So let's just point that out, because this is going to be important in the problem. Here, my domain is all real numbers except 1 and -1. So my domain goes from negative infinity to -1, and then from -1 to 1, and then from 1 to infinity. So -1 and 1 are going to be important in this problem, because we need to keep track of what's going on around them, knowing that they are not defined at those values. The function is not defined at those values. So first thing I did here was I rewrote y as -1, 1 minus x squared to the -1. And the reason I did that is to avoid using quotient rule when I take the derivative. The way I wrote it allows me to use just chain rule. So in the next line, I multiply -1 by the negative on the outside of the binomial, so it becomes positive. Subtract 1 from the exponent, so I get -2 as an exponent. But then you have to multiply by the derivative of the inside, and that derivative is -2x. So in the next line, I just rewrote it in a different way. So we want to solve -2x over 1 minus x squared to the second power, and that's what we set equal to 0. So to solve an equation like this, you're really just solving the numerator. So -2x equals 0 means that x is equal to 0. So I have one potential maximum or minimum value, but here we actually have 3 critical points. We have the restrictions to our domain, 1 and -1, as well as the solution to f prime, which is 0. So when I write my number line to keep track of these numbers, put them in order, I write -1, 0, and 1. And now we must pick our test points. And so this time we're going to have to pick 4 different test points, because there are 4 intervals. So I pick a number less than -1, and again, it doesn't matter what you pick, but suppose I pick -2. If I take -2 and plug it in here, my numerator turns positive, and my denominator is always positive no matter what. And the reason we know that is because my denominator is going to get squared. So if the inside is positive, squaring it keeps it positive. If the inside is negative, squaring it also keeps it negative. So if the numerator is positive, the whole thing is positive, which is why we show that y is increasing. Then we pick a number between -1 and 0, such as -0.5. Again, if you plug it into y prime, you get that it's a positive result as well. It means the function is also increasing. Now we pick a number between 0 and 1. Again, pick anything you want. You could pick a half, a third, 2/5, it doesn't matter. If you plug it in to the first derivative, you'll get a negative result. And if you pick something greater than 1, you also get a negative result, which means that the function is increasing from negative infinity to negative 1, and then from negative 1 to 0. Remember, it's undefined at negative 1, so you want to make sure that you separate out those two intervals. And it's decreasing from 0 to 1, and then from 1 to infinity. And again, it's not defined at 1, so you need to separate it into two separate intervals. So that means I have actually just one extreme value. We have a maximum at 0, and when x is 0, y is negative 1, you're plugging back into the original function here at the top in order to figure out what your point is on the graph. So when x is 0, plug that in here into the original function, you get that your y is negative 1. And that's a maximum because in the interval before 0, the function is increasing. In the interval after 0, the function is decreasing. So if you are increasing, then decreasing, you definitely are going to have a maximum value. Okay, so let's see what our second derivative will tell us. So second derivative means that I must take the first derivative, which I wrote here, and then I have to take the derivative of that to get the second derivative. Since my second derivative is a quotient with a variable in the numerator and the denominator, I'm just going to go ahead and use quotient rule. So here on the right, I wrote out the parts for quotient rule. So f is my numerator, that's negative 2x. F prime is negative 2. G is my denominator, 1 minus x squared to the second power. And g prime, here I have to use chain rule. This will be 2 times 1 minus x squared times the derivative of the inside, which is negative 2x. And so my g prime is negative 4x times 1 minus x squared. All right, so now we put this all together. Remember, you have to multiply g times f prime first, and that's what you see here, right below this. So g times f prime minus f times g prime all over g squared. And so g squared will be 1 minus x squared squared, and then you have to square it again. That's what the formula tells you to do. Okay, so now we're ready to simplify the numerator. In order to simplify the numerator, the quickest and easiest way to handle this is to factor out the common binomial. The numerator has 1 minus x squared in common in both products. So if I factor that out, 1 minus x squared goes in front of this bracket. And then the first product is just negative 2 times 1 minus x squared, which is negative 2 plus 2x squared. And when I factor 1 minus x squared from the second product, I'm only left with minus negative 2x times negative 4x, which is a minus 8x squared, all over our denominator. And so when you have an expression squared, it just becomes to the fourth power. All right, so that means that 1 minus x squared on the outside of the numerator cancels with 1 in the denominator. And the expression inside of the bracket right here, there's like terms. So we're left with negative 2 minus 6x squared all over 1 minus x squared to the third power. So similar to what I explained before, in order to solve this equal to 0, we're only solving the numerator. Again, keep in mind that negative 1 and 1 are not in the domain. So I have negative 2 minus 6x squared equals 0. Add 2 to both sides, divide by negative 6. You have x squared equals a negative number. A negative number does not, when you have to take the square root of a negative number, you do not have a real number solution. And anything you want here when you're graphing on a Cartesian coordinate system should be real numbers. So basically that means you're not going to find an inflection point here. But that doesn't mean you can't figure out your intervals of concavity. So in order to figure out the intervals of concavity, I still need to keep track of what's happening to the left and right of negative 1 and 1, as well as in between. So to the left of negative 1, if you pick a test point and plug it into your second derivative. So here you're plugging it in right here. So if you pick something like -2, if you plug that into your function, the numerator is negative, but our denominator is also negative, so two negatives make a positive. That means that it is concave up from -infinity to -1. If you pick a number between -1 and 1, the easiest choice is 0, and plug it in to the second derivative, you'll get a negative on top, a positive on the bottom. That means it's a negative result, which means the original function is concave down. And then if you pick something greater than 1, like 2, you also get a positive result. So it's also concave up from 1 to infinity. So that information is here in the box. Concave up from -infinity to -1, and then from 1 to infinity, and it's concave down from -1 to 1. And so as I mentioned before, since the second derivative has no solution, there's actually no inflection point for this problem. So this is the graph here on the right. So remember, the graph, the first derivative said that the graph would be increasing from -infinity to 1. So you see that here. And increasing from -1 to 0. So that's right here. Decreasing from 0 to 1. So that's this portion here in the middle, and then decreasing from 1 to infinity. And we have a maximum point at 0, -1, which we see right here. Now let's see if our concavity matches up with the graph. So recall, concave up from -infinity to -1 and from 1 to infinity. So these two pieces here, these are our concave up part. And the part in the middle is the concave down part, which we see here, concave down from -1 to 1. So that's this upside down part that looks like a parabola. And so we get a good sketch from using our first and second derivative. So now you should try doing 4.3 homework.